This is a continuation of chapter 2.3 of the Good Science textbook, keys 9 and 10, on graphic motion. I'm going to continue my discussion on how to go between graphs. So suppose I want to go from the following graph, acceleration time graph, meters per second squared. I want to go from here to, let's say, a velocity time graph. And then from there to a displacement time graph. Okay, let's do this one step at a time. I'm going to make up some numbers. Hopefully they're correct. Okay, acceleration time graph. Suppose I have this. So 4 seconds, 8 seconds. I've got 0 here. Acceleration is 2 meters per second squared from 0 to 4 seconds. And then from 4 to 8 seconds, it's 0. Drops down to this. How do I interpret this? Suppose I give you this in an exam and I'll say, interpret this for me. What does it mean? Well, this is basically a step graph because it looks like a step. You've got constant acceleration of 2 meters per second for 4 seconds from 0 to 4. Then all of a sudden, let's suppose you take your foot off the pedal, you're driving a car. The acceleration goes from 2 straight down to 0. Suppose I slam the brakes really hard. Okay, you got to picture what's happening here. I'm in a car. Think of a car. I'm accelerating, constant acceleration. My foot's down on the pedal. Going up to 2 meters per second squared. So I'm gradually increasing the speed, but then I slam the brakes. Okay, that's what this graph is showing here. Now, going from acceleration to velocity. Now, acceleration is a vector. I should be putting an arrow on top, but anyway. Vectors, if you remember, they're things that are numbers, but with direction. Now, acceleration is a vector, and velocity is a vector as well. Okay, they've got arrows on top. Okay, vectors are like arrows in space. If there's wind coming in at 20 km per hour from the north, think of a whole series of arrows coming in from the north at 20 km per hour. Okay, and displacement as well. Displacement is distance but with direction. So velocity is speed but with direction. It's the same thing as speed but with direction. And displacement is the same thing as distance but with direction. Anyway, so how do we go from acceleration to velocity? We need this. Acceleration is the change in velocity v over the change in time. Okay, that's just in other words, the final velocity minus initial velocity over the final time minus initial time. Remember, delta means change in. It's Greek. It's used a lot in maths and physics. If it was delta capital T, it would be the change in temperature. Okay, that'll be final temperature minus initial temperature. So to work this out, so to work out, in other words, delta V, we need to do A times delta T, if you rearrange this expression here. So in other words, we need the area under the acceleration time graph to work out velocity and time, right? Because mathematically it's that. So the area, so the time doesn't change, right? Let's put the time back again here. The area under region 1, let's call that. The area of a rectangle in this case. So that's 4 there. Length and the height is 2. 4 times 2 is 8. So the area for 1 is 8 meters per second. Why is it meters per second? Because 2 meters per second squared times by 4 seconds, the seconds cancel out. The seconds squared and the seconds cancel out. You're left with 8 meters per second. Okay. So you get 8 meters per second for 4 seconds. So the velocity from 0 to 4 seconds is 8 meters per second. So let's do 8 minus 4 minus 8. Remember, you can have minus velocity. It just means, so minus 4 meters per second means you're moving at 4 meters per second in the opposite direction. So 8 meters per second from 0 to 4. It looks like that. It's a flat line. Okay, you're moving at constant velocity from 0 to 4. Now, from 4 to 8 seconds, the acceleration is 0. If there's no acceleration, the velocity stays the same. I'll say that again. Acceleration by definition is the change in velocity, but since there's no change in, since the acceleration is 0, you're moving at constant speed, your velocity, your speed stays the same. So it's just 8. Continues all the way to 8. Oh no, my apologies. No, it should be like this. Apologies for that. Yes. Yeah, ignore what I did before. My apologies. The reason being is because the velocity increases linearly in a straight manner like this from 0 to 4 seconds, and then at 8 meters per second, and then it stays constant at 8 meters per second. So from 4 to 8 seconds, if you recall, the acceleration was 0, which means the velocity is constant. So it's a flat line like that. If you take so acceleration is velocity over time. If you take the velocity here, 8, and divide it by the time, which is 4, you get back 2 meters per second squared, which is up here, flat line. That's why it has to be a straight line like that. Okay, and then it's flat after that. Okay, how do we go from here to a displacement time? If you recall, displacement or distance, so displacement with an arrow on top is speed, velocity, times time. Remember, speed equals distance divided by time. To get distance or displacement in this case, you multiply the speed v by the speed s by the distance by the time t, and you get this. You need to find, in other words, the area under the velocity time graph. Let's go back up to it here. Break it up into segments. There's 1 here and there's 2 here. There's a triangle and a rectangle. So the time stays the same, 0 to 4, and then 8. So from 0 to 4 seconds, that's a triangle there. The area of a triangle, back to basic maths, is a half times base times height. Half times the base is 4, that thing here. The height is 8, that thing there. Half times 4 times 8 is 16 meters. And for segment 2, the area of a rectangle is just the length times breadth, length times height, in other words. I haven't graphed it yet, I want to show you why. Length here is 4 because the difference between 8 and 4 is 4. And the height is 8 up here. So 4 times 8, that's 32 meters. Now, the total displacement is 16 plus 32, which is 48 meters. That is the total displacement, the total distance traveled from your starting point to your finish point. Your graph is going to look like a curved shape. Okay, because the object is accelerating by definition here. If the object is accelerating, you're covering a certain amount of displacement, a certain amount of distance, non-linearly. Okay, you're covering a lot of ground. If you think of a car, I'm stationary in a car, not moving. If I all of a sudden put the accelerator on really rapidly, I'm covering a lot of ground sort of exponentially. That means I'm not covering it at the same rate every, let's say, 2 seconds. It's rapidly increasing. So it looks like this. I might cover this amount of ground, and then that much, and then that much. So it's getting bigger and bigger. That's called an exponential. So your graph would look something like this. So from 0 to 4 seconds, so I should mention here, let's go up by tens, 10, 20, 30, 40, 50. From 0 to 4 seconds, I'm going to get a curved line because the object is accelerating. Okay, if you look here, 0 to 4 seconds, it's accelerating. So from 0 to 4 seconds, you've got 16 meters, right? So it increases rapidly to 16 meters like this. So you start here at 0, increase rapidly to about 16, which is there. Then from 4 to 8 seconds, you get a straight line. You get constant velocity here. Okay, constant velocity means it's a velocity, you're moving at the same velocity, 8 meters per second. So from 4 to 8, it's a straight line, it's constant. Straight lines look like this. So it looks like this, and then straight like that. And that's it. I can quickly go over it again. Acceleration versus time. Suppose you start off with this step diagram there. We know that acceleration is the change in velocity over time. It's how fast your speed is changing, your velocity. These are all vectors. Acceleration is a number with a direction. Velocity is a number with a direction. And displacement is a number with a direction. From 0 to 4 seconds, you've got constant acceleration. If you've got constant acceleration, it means your velocity is increasing. So you get a straight line like this. However, from 4 to 8 seconds, your acceleration is 0. That means your velocity is constant, the same, so it becomes a flat line. Then, to go from velocity time to displacement time, you use this relationship here. Displacement, which is the same thing as speed really, is velocity, which is speed. Displacement, which is distance, is velocity, which is speed, times time. Okay, using speed as distance divided by time. From 0 to 4 seconds, you need the area under the graph to work out displacement. That's a triangle, half BH. You get 16 meters. You get a curve because you're accelerating. If you're accelerating, you're covering an unequal amount of ground every, let's say, every segment of time. In every segment of time, let's say a couple of seconds apart. However, from 4 to 8 seconds, your speed, your velocity is constant and your acceleration is 0. Okay, if your velocity is constant, your change in position over time is constant. Okay, you're traveling at the same speed, you're covering an equal amount of ground, and that's how you do that.